Hello, everybody. My name is Joe Caggiano, and thank you so much for watching my talk today on multifluid magnetohydrodynamic investigations of Earth's magnetosphere during geomagnetic pole reversals. So, geomagnetic pole reversals occur relatively regularly throughout geologic time, but a reversal event has not yet occurred in recorded human history. However, these reversal events have potentially significant effects on Earth, such as increased cosmogenic radiation, an increase in atmospheric loss rates, and also potential effects on migratory species and especially modern human technology. However, observational paleomagnetic data during a reversal event is difficult to resolve for understanding of a topology, so we're not sure what the magnetic field actually looks like during these reversal events. We're basically left with modeling, and we have magnetohydrodynamic geodynamic models, notably Glatzemer and Roberts in 1985, which reveal that during a reversal event, the dipole moment of Earth essentially disappears, and you're left with higher order magnetic moments which become more dominant. And from a near-Earth space environment perspective, the quadrupole moment decays the least after a dipole with respect to radius, so therefore it becomes the dominant magnetic moment in Earth's magnetosphere. So there has been previous research on a quadrupole magnetosphere in the past. Vogt and Glatzmeyer back in 2000 examined trapping centers of high energy particles calculated for various quadrupole geometries, which we'll look into later. Vogt et al. 2004 looked at tail currents studied using an ideal magnetohydrodynamic Riemann solver, also known as Batz-Russ, and you can see that on the figure on the left here. And essentially, the results from that MHD study revealed a dramatically different magnetospheric convection profile than what you see in today's dipole. However, there is limited interpretation of this new convection profile because the main focus of the Vogt et al. 2004 study was on tail current systems. So the quadrupole field topologies that Vogt and Glatzmeyer used are based on this eta parameter, which is a ratio of Schmidt coefficients used in the spherical harmonic expansion of a quadrupole. And this eta value can be anywhere between -1 and 1. However, for the purposes of this study, we'll use the eta equals 0, 0.5, and eta equals 1 case. And the negative values are essentially the same geometry, but with opposing magnetic moments. And you can see the topologies of these on the top of the slide. So the eta equals 0 case is essentially a fully axisymmetric quadrupole. The eta equals 0.5 is essentially the same as the eta equals 0, but it's stretched along one axis. And the eta equals 1 case is essentially stretched so much one axis that it actually sort of pinches off on either side of the quadrupole field. So you sort of have a convergence of magnetic field right at the center of Earth from this perspective here. So the magnetic equatorial surfaces or trapping center surfaces that Vogt and Glatzmeyer came up with are significantly different for a quadrupole, as you can see, than they are for Earth. In Earth's current magnetic field configuration, the magnetic equator is on or at least very close to Earth's rotational equator. During a pole reversal, however, more than one magnetic equator exists, as you can see, and they essentially collide with Earth at around the mid-latitudes. And also these magnetic equators are non-planar in some cases as well, which adds some additional complexity. So back in 2019, we revisited the Vogt et al. 2004 quadrupole convection topology from an analytical perspective for the sake of looking at the plasmasphere stability in an analytical case. And essentially what we found is that the quadrupole fields can be expressed as essentially two stacked oppositely oriented dipole moments, where one hemisphere of the quadrupole is essentially a closed convection system, and then the other hemisphere is essentially an open convection system. And each hemisphere will essentially have an opposing convection flow. And the convection electric fields derived from this consistently remain oriented in a similar direction as the quadrupole. So they remain oriented along those trapping center surfaces that we saw in the previous slide, which in this case is oriented directly out of the screen. And then just to give you further perspective of how the convection actually works, here is a diagram showing how the magnetic footprints travel through the ionosphere as they convect around a quadrupole. So essentially you see really strong flows along the equator of Earth as the magnetic field essentially moves along and convects. And you can see in the closed convection region here, we have a dotted line indicating that the closed convection is a little bit weaker just because there isn't as much energy being deposited into the closed magnetosphere due to the orientation of the reconnection points. However, you do see oppositely oriented magnetic flows in the magnetosphere. So just to refresh on what the electric fields look like in the inner magnetosphere and how they affect plasmasphere motion, etc. Here is a reminder of what the dipole looks like. We're looking at the log of our KE ratio, which is basically a ratio of the corotational electric field over the convection electric field. And essentially anywhere that's in the blue is convectively dominated, so it's convecting towards the subsolar magnetopause. Anything in the red is co-rotationally dominated, so it's co-rotating with Earth, and that's anything that's co-rotationally dominated is within the boundary of the plasmasphere. And you can see a little stagnation point created on the duskward side there. So for the magnetic quadrupole, you do see similar structures that you saw to the dipole case, except now instead of being oriented along the geographic equator, they're oriented along the magnetic trapping center surfaces at the mid-latitudes. Essentially here you still see in the open convective region, you still see a sunward convection with a co-rotationally dominated area near the Earth with a stagnation point sort of in the middle on the duskward side. However, in the southern hemisphere, you actually see the opposite flow because that's the closed magnetic convection region. And you'll see a tailward convection there, and you'll see a stagnation point on the dawn side of Earth, or the co-rotational and convective flows oppose each other. For the 8 equals 0.5 case, it's essentially the same as the 8 equals 0 case, except the field is elongated in one axis. So the stagnation points will be slightly further away, depending on which way it's oriented, or they'll be slightly closer. However, it's pretty much the same structure. For the 80 equals 1 case, however, this is where things get a little messy. So you still see opposing convective flows depending on which hemisphere you're in. And you do see stagnation points form in this case. However, because the trapping center surfaces converge, at that point, the co-rotational flow essentially disappears completely, and you get a complete erosion of the plasmasphere at those points. So the plasmasphere is essentially unstable beyond a half a draft period. And you can see that here when the field is rotated opposite direction. And the other point is that the field rotates. So these trapping center surfaces are constantly oscillating, on a 24-hour period, which will interrupt convective flow. It'll interrupt co-rotation of the plasmasphere. So it essentially becomes a very turbulent and messy system. The goals of this study are to examine the quadrupole fields using a multifluid MHD model, and then compare the results from the multifluid model to our analytical results and from those of previous works. And essentially we're going to accomplish 3 goals from that. So we're going to examine the convective flows of geometries and compare them to the canonical Dungy cycle of a dipole. Also compare our results to our previous works. We're going to compare the ideal single fluid MHD magnetotail currents simulated by Vogt et al. 2004 with our multifluid simulations to evaluate the differences between these simulation formulations applied to the quadrupole fields, and also assess differences in ionospheric flux between the dipole and quadrupole fields using the outflow rates as an analog for determining changes in atmospheric loss during pole reversal. So the multifluid MHD model that we're using, it was devised by Robert Wingley, and it has been implemented at Earth, Ganymede, and Uranus. And the Uranus one was particularly successful because it indicates the usefulness of the model for analyzing unconventional magnetospheres such as a quadrupole, because Uranus's field is a mess. The model essentially simulates bulk plasma in the fluid dynamic limit, excluding high energy plasmas, and it treats each ion species, which in this case we're using hydrogen ions, oxygen ions, and essentially a bulk solar wind, as an individual fluid simulated. And then electrons are considered to be in a steady state and quasi-neutral with the ion species, so the electron timescales are much faster, so they are considered just in equilibrium with the ion species as the model progresses. And the solar wind conditions that we're using for these models are -5 nanotesla, 6 centimeter cube density at 400 kilometers per second. So a relatively quiescent solar wind for simulating steady state convection. Getting to the results. For our 8 equals 0, we actually find a very similar convection profile to what was predicted and what Vogt et al. 2004 showed in their model. So in this case, the magnetic field orientation is actually the opposite. So the open convection field is in the southern hemisphere, and the closed convection region is in the northern hemisphere. And you can see a subsolar magnetopause right here. You'll see a tailward reconnection point right here, and then you'll also see a third reconnection point in this general region right here. So very similar to what we were examining before. And then also keeping in mind what the magnetic equatorial surface looks like, if we examine the convection flow along those points, what we find is that the co-rotational region in the closed trapping center surface is actually very, very strong. And again, this goes back to the limited energy deposition due to the orientation of the reconnection points. So essentially you see very little convective flow within the closed field, but it's essentially mostly co-rotational along that equatorial, or the trapping center surface. And then in the open trapping center surface here, you do see strong sunward convection along that surface as well. So you see convection on both sides, and then you see a small region going to about 2 or 3 Earth radii away from the center of Earth, showing a co-rotational point where the plasmasphere is present. For the 80 equals 0.5 case, you do see a very similar topology as the 8 equals 0 case. Essentially, this orientation is elongated, it's oriented so the elongated axis is in the dawn-dusk region. But again, you do see a sunward reconnection point, a tailward reconnection point here, and then a high latitude reconnection point right up here. Again, with the 8 equals 0.5 case, looking at the closed trapping center surface, you do see a very strong co-rotationally dominated area. However, you do see stronger convection regions on sort of the outer boundaries of this region around here after about 3 Earth radii on the downward duskward sides, indicating that there is some convection present due to the elongation of the field. And then in the open trapping center surface, again, the convection region is way more pronounced, and then you have a sort of a turbulent boundary layer region here, followed by a co-rotationally dominated region further inside at about 2 to 3 Earth radii. And then for the quadrupole case, this is where things get really messy. So we have our quadrupole oriented, so the trapping center surfaces, the convergence of those are essentially facing sunward and tailward respectively. Again, here, looking at the flows along the trapping center surfaces, there is a lot of turbulence. And essentially, as you can see, there really is no co-rotational field that is allowing the plasmasphere to exist. It's essentially very unstable. You do see a little bit of convection in the open region, moving towards the center of magnetopause here on the very outside, but essentially on the inside, it's incredibly turbulent. And many of the processes that you would see otherwise are being interrupted due to the oscillation of the magnetic field and just the nature and the structure of the magnetic field itself. So now looking at the currents for each quadrupole magnetosphere, we do see some very interesting structures forming. At the magnetopause boundary, we actually see a higher order structure of Chapman-Ferraro currents. So essentially you see 3 current loops form. You see sort of this central current loop forming here, and then you see an oppositely oriented current loop at the high latitude regions, both on the north and the south sides of the magnetopause, which is really interesting. And you sort of see that reflected in the tail currents as well, where you sort of have a higher order structure forming. You essentially get 2 really strong current sheets forming at plus or minus 5 Earth radii, but then you see additional current loop structures along the north and south field, and then also along the sides as well. And then for the 8 equals 0.5 case, you essentially see basically the same structures, although a little bit different just because the orientation of the field is different. But essentially you see that 3-part Chapman-Ferraro structure on the magnetopause. And then again, you do see a formation sort of 2 current sheets along with several current loops in the tail. So even for the 8 equals 1 case, you also see a similar higher order Chapman-Ferraro current system and along the magnetopause boundary here. And for the current density down tail, you do see sort of a convergence of those current sheets that we saw in the 0 and 0.5 case. So you sort of see a merging and convergence of those currents right here, in addition to the eddy current loops that you see along the side, both on the north-south region and then on the east-west region. And all of these current densities in the tail, they are consistent with the results from the Vogt et al. 2004 study. And finally, looking at atmospheric loss, essentially we looked at the ionospheric escape in a region around Earth, basically by generating a sphere and calculating the outflow through the sphere and integrating it. And essentially what we find is that for our dipole control model, for the 8 equals 0 and the 8 equals 0.5 model, they all fall within sort of an observed dipole outflow range of atmospheric flux that you would expect. So you do see in the 8 equals 0 case, it's actually a little bit more stable than our dipole control case, but it is within normal regions. However, the 8 equals 1 case is outside of this region, so you are seeing a stronger atmospheric flux or atmospheric loss in the 8 equals 1 case, which is to be expected considering how turbulent and unstable the magnetospheric structures are in that topology. However, these low values might also be due to the quiescent solar wind that we had in the model itself. So essentially, I will just go ahead and leave the conclusions up here. Thank you so much for watching. If you have any questions, feel free to visit the Q&A session in room 352 on Thursday at 3 p.m. Or you can feel free to email me either before or after the conference at jcajian@uoregon.edu. Thank you again so much for watching, and I'll just leave my references up here. I appreciate it.